In this video, we're going to define formally what indefinite integrals are. So in the last video that we saw, I'll cover this up, we talked about the fundamental theorem of calculus, and we saw that when we integrate over our derivative function, we get out the original function again. And this is where little f is the derivative of our capital F function. And last time we evaluated some of those definite integrals that had numbers on its bounds. And now we're going to introduce the idea of indefinite integrals. So this is exactly the same, maybe I should say, last time we did something like the integral from 2 to 3 of x squared dx. We were able to apply fundamental theorem of calculus, and we were able to anti-differentiate the inside function. By anti-differentiate, we're going back to our previous section, and that becomes 1/3 x cubed plus c. And I can tell that this is an antiderivative because when I take the derivative of this using power rule, the 3 multiplies with the 1/3 to get no coefficient, and the power drops down to b squared. So I can check, maybe I'll write that down, check by taking the derivative. And we applied fundamental theorem of calculus to say that this is the same thing. I'm going to evaluate it as x equals 2, which is my bottom value, to x equals 3. So this will give me a definite integral of, plugging in the 3 value first, we get 1/3 of 3 cubed. That's 27 divided by 3, which is 9, plus c, all minus, when I plug in x squared, I get well, maybe 1/3 of 2 cubed plus c. So this becomes 9 plus c minus 8/3 minus c gives us a value of 9 minus 8/3, which is a number. This is just review, but I think it's a helpful review. So what happens if I don't have bounds here? Now I'm just taking an antiderivative, and this is something that we did before in 4.7 exactly. I'm going to use polynomial rule, and this becomes 1/3 x cubed plus c. So the only difference is, and I'll write this maybe in a different color, this is a function of x. And generally, indefinite integrals are always functions. And they always have the plus c. Whereas definite integrals are specific numbers. Like this messy number, 9 minus 8/3, which is 27, which is 19/3. And there is no plus c. So in your online textbook, they have a table. Hopefully I won't get any copyright trouble for putting this table up. Just don't tell anyone, right? It's on the internet, no one will know. Of a whole bunch of the antiderivatives that they want you to use. So here's a summary of some of the properties that we talked about in the previous section, as well as this is messy notation for power rule. It just means that when I take an antiderivative, I add to the power, and I divide by 1 plus that power. What I want to highlight, though, is that there are a couple of these rules that we aren't going to have to worry about in this class. So you do need to know that the antiderivative of e to the x is e to the x, but we aren't going to worry about alternate bases. This is something I might put on a homework, but you won't have it on exams. Similarly, we aren't going to worry about hyperbolic trig functions. Those are things I don't care about. I also, the rest of these I do think are important though. So the antiderivatives of inverse trig end up being very important, and these antiderivatives, maybe I could put these sort of in quotes, that these are less important typically, but the rest of them I do want you to have in your tool belt to be able to use to call upon whenever you would like.